Good day! I'm Dr. T and welcome to my office. So today I would like to talk about compounds and how they're built at the atomic level. So when we're thinking about compounds, we're thinking about things that are made of two or more different types of elements. And actually what I'm describing doesn't have to be a true compound. It could be an element. Because really what we're talking about today is how you attach atoms to each other. There's typically three major ways of doing this. There is actually some recent research looking at the potential of a fourth way. I haven't jumped into it, and we're just going to kind of stick with the three common approaches. So those are going to be ways you would bind metals and metals together, ways you would bind nonmetals and nonmetals together, and ways you would bind a metal with a nonmetal. So let's go with the double metals. So in this case, we've got multiple metal atoms. These could be of the same element, or quite often they're going to be different elements. This is going to form what we call a metallic bond. And in a metallic bond, you're going to have the metal atoms, and they're going to be hanging out, but they're going to share some of their electrons with the group. It's going to create what we call an electron sea. So one or more electrons from most of the atoms, not necessarily all of them, are going to be shared communally. This gives the metals most of their properties. They're shiny because these electrons can interact with light in any old way because there's so many electrons and so many atoms that they can find really cool pairings somewhere to do something with that particular photon. Additionally, they're going to be great conductors because those electrons can get up and move. If you recall, electricity is the move of charge, such as electrons. And the same goes for heat. You can get things vibrating, and you can vibrate the heat through it quite nicely. Of course, metals do this differently. So some metals are better conductors than others. So I shouldn't imply that they're all wonderful conductors, although typically this does make them a pretty good conductor. Additionally, when you're looking at the other properties such as malleability, ductility, because they're sharing the electrons communally, if you start moving them around, well, they're still sharing. They're just sharing from a slightly different spot. And metals typically can, be shuffled around a little bit more so than other ways of attaching atoms to each other. Now, when we look at nonmetals, they do things very differently. Instead of having this electron sea, they are going to share electrons in what we call a covalent bond, but typically it's between one atom and another. There are cases where they will share some electrons communally, but those are not all that common and specifically reference certain types of carbon compounds. But typically what nonmetals are going to do is when they form bonds, they're going to form two atoms sharing a pair of electrons, potentially up to 3 pairs, even 4 pairs in a couple of rare cases of electrons between each other. But typically it's going to be 2, 4, or 6 electrons total. Now, the sharing does make them a bit more brittle, because if you try and move them past each other, well, if you've ever been in a long-distance relationship, you know those don't work that well. You can do it, but the atoms can't. And when they're trying to share their electrons, if you pull the atoms a little too far apart or try and twist them into the wrong configuration, then the electrons will break apart and they will go with one atom or both, and you no longer have that bond. Additionally, the electrons can't go flowing through it, so typically speaking, nonmetals are terrible conductors, apart from certain carbon compounds such as graphite, which does its own kind of interesting thing. These guys can arrange in a couple of different ways. Whereas metals, because they were sharing all the electrons around, they would just kind of be one giant thing, usually arranging the atoms in a three-dimensional pattern, what we call a lattice. The covalent bonds, those can do a couple things. One, you can do this whole lattice thing where you have this kind of network of organized repeating patterns of atoms, each sharing with the other ones. And you'll see that in things like diamond. This is what we call a covalent network solid. However, they don't actually have to be all that organized, and you could have them in kind of a random hodgepodge, which will give you an amorphous covalent network solid, something like glass. Alternatively, though, you don't have to have them all interconnected in some fashion. Most covalent compounds form what we call molecules, and molecules are going to be discrete clumps of atoms. So imagine, say, an oxygen sharing a pair of electrons with a hydrogen and another pair of electrons with a second hydrogen, and that's all the sharing that's going on, and you now have a water molecule. These now are going to be their own individual particles, and they're going to kind of bounce around and do their own thing. They might align themselves up into a regular repeating pattern, such as you would see in ice, or they might not, such as you would see in water or steam. The third way that I'm going to discuss for atoms to interact with each other is typically seen, although not always, when you have metals and nonmetals interacting. In this case, we have what we call an ionic bond. And I use the quotes because true bonds are going to be ones where electrons are shared, and ionic bonds, typically the electrons are not shared. So in this case, some of the atoms, typically those that are metallic or the metal side, are going to lose electrons. And they may lose electrons to their partner, or they may have lost them at some point in the previous past. This will now make them cations. They are positively charged since they've lost their negatively charged electrons. The other atoms, typically those that are the nonmetals, are going to acquire electrons. Once again, they could have acquired them from the metal, or more likely they've acquired them at some point in the past. These are then going to become anions, negatively charged atoms. They're negatively charged because, remember, they have a surplus of negatively charged electrons. Well, opposites attract. Cations will attract anions, and, well, they'll hang out. This typically then results for, with the case of solids, a regular repeating crystal structure, aka a lattice. Ionic compounds typically are very solid, very hard, but brittle, because if you disrupt this lattice, you're going to go, instead of having some form of alternating pattern of positive next to negative, it'll be a negative, negative, positive, positive, and those don't want to hang together. So it's going to take a lot of force to do that, but once you do, they tend to crack. It also tends to be that these guys have very high melting points, although that's not always the case. Now, when looking at these compounds, it is an important thing to keep in mind, not just how they're interacting, but who is interacting with whom and in what ratios. With the exception of the molecules, you have thousands upon thousands of atoms of each type in even a tiny grain, because remember, atoms are really tiny. So instead of trying to describe how many atoms of each type are there, typically we use what's known as an empirical formula. So an empirical formula takes the chemical symbol of one of the elements, typically the ones that are more left and down on the periodic table, uses a subscript number to describe how many of them are in the ratio, and then the next symbol for the next element and its subscript. This is then going to give us a whole number ratio of how many elements are in there. So if I were to have, say, some calcium chloride, I would have 1 calcium for every 2 chlorines. I'd have CaCl2. There is no 1 below the Ca because that's assumed. And we typically don't write 1s, saves a little bit of ink. If I have sodium chloride, good old table salt, that would be NaCl because it's a 1-to-1 ratio, and once again, we don't write 1s. That said, there are cases like red rust where it would be Fe2O3, meaning that there are 2 irons for every 3 oxygens. Now, for molecules, it's a slightly different story, because in this case, these are their own discrete clumps, and in a single molecule, there is a specific number of atoms. For instance, if I have a molecule of glucose, there are 6 carbons, 12 hydrogens, and 6 oxygens. This is a ratio of 1 to 1, and I could say the empirical formula, my formula based on ratios, would be CH2O, but it would be somewhat more informative to tell you that, no, there actually are 6, not a ratio of 6, just 6 carbons to 12 hydrogens to 6 oxygens. This isn't a ratio, this is a count. And in that case, we have the molecular formula. Molecular formulas only apply to molecules because everybody else forms a lattice where it's not a fixed number of atoms, it's a fixed ratio. So with that said, I'll see you in the next video. Have a wonderful day.